Recently, a lot of talk has been made about Bayesian reasoning and Bayesian statistics. This also has increased while the library PyMC3 has reached more audience. Bayesian statistics is a general topic which is very good to know, and because you think in a Bayesian way almost every day and every minute. We just don't think about the mathematical rigorness about it. So Bayesian reasoning is something that we all share and we all practice on an actual daily practice, because whenever you update your beliefs, whenever you see something, you see some data and then you update your beliefs based on this data. This is everyday Bayesian reasoning. And you're already a Bayesian statistics, even before exploring any of this data and topic. In statistics, we use some special calculations and we do this much more accurately, and this is what we are going to explore. We are using probabilities and we are using numbers to denote these probabilities. This is much more rigorous and much more correct, and knowing this rigorous mathematics will help you in many ways while doing your daily job as a software engineer. Let's take an example. You wake up in the morning and you don't find your mobile phones. What do you think are the options for this? I would say that let's consider an option where your mobile phone was eaten by your cat, and your cat has run away with it. Basically, your cat has stolen your mobile phone. He has also become addictive to your mobile phone. He took it and went away. Okay, so this is like some general thought that you have about the world. And by only thinking this thought the minute you woke up, and the fact that you just woke up from a dream might explain this thought that you think that your cat stolen your phone and ran away, you have done a full Bayesian cycle. Because one, you observe the data. Which data did you observe? That your mobile phone is not beside you, right? So, and two, you formed a hypothesis. What is the hypothesis that you have formed? It's you, it's not me that formed this hypothesis. You have formed a hypothesis that your cat has stolen your phone and run away. And then you are beginning to update your beliefs based on the data, because you are beginning to search the home and search for your cat, and based on your findings, you will update your beliefs. This is almost like a full Bayesian cycle, only we didn't use any probabilities and any letters denoting the probabilities that we think that these events have happened. Let's consider for a minute the data. The data that we have observed is that we can't find our phone, and also that we can't find our cat. The fact that we can't find both of them is rather surprising. I mean, you don't wake up every morning without your cat and without your phone. So let's begin to mathematically rigorously denote this. So the fact that you can find them is P, the probability of not having your phone and not having your cat is very low. Why is it very low? Because we already said that it is surprising. So P is the probability, and in brackets we put the evidence that we have seen. We have seen that we can't find our phone and we can't find our cat, both, and it's surprising. So the probability that both of them happened and that the phone has stolen the cat has stolen our phone, the probability of this is very low. So it's surprising. So the probability that our cat has stolen our phone and ran away is very low. This is surprising. Vice versa, let's say that the probability that we have simply woke up and our phone would be beside us is pretty likely. So we can denote that with probability P, open brackets, that the phone is beside us when we wake up is likely, which means it has a very high chance of this happening. We believe that it has a very high chance. Let's move on to the next topic, and it is about prior beliefs and conditioning probabilities. When we wake up in the morning, we have prior beliefs about the world. We know that cats do not talk usually on the phone, cats do not steal phones. Okay, we have some prior beliefs and we know that phones get lost. And with those prior beliefs, we went to bed and we woke up. So now we can say that P, open brackets, P, the probability that both our phone and our cat disappeared at the same morning, conditioning, this is like a pipe, our experience on Earth is very low. Okay, so the probability that both the phone and the cat would get lost on the same morning is very low, but we condition this, that's why you see the sign pipe in the conditioning on our experience on Earth. This is called a conditional probability, meaning we don't only say the probability of our phone and our cat being lost, we say the probability of our phone and cat being lost conditioned on our experience on this planet. And this is very low. And we mark and we denote this condition with the pipe. As for the data that we are seeing, so the data is what we actually see on the world. We denote this with capital D, and the capital D is what we actually see. This is the data that we look on. The data was that we don't see our cat and we don't see our phone. This is the data. And the capital X is the usual experience, what we experience, all our priors, our priors experiences. So we know from our prior experiences, this is the capital X, that cats do not usually talk on phones and they don't have special affiliation for stealing phones. Capital X, our experience, our past experience. Capital D is the data that we see. And now we can formulate this much more concisely. And this is the mathematical rigorousness that we talked about. This is P, open brackets, capital D, conditioned on X. So this is P, D pipe X. Okay, imagine you say, we look at P and then in open brackets, like opening a function, you have a capital D and then pipe X. This means the probability of the data that we have seen conditioned on our prior experience. And this is our notion about this probability from our prior experience, what we think the probability is. And thus you can already say in mathematical rigorousness, what is the conditional probability? The conditional probability is P, probability, capital P, brackets, like function brackets, and then the data conditioned pipe on the experience of yours, X, capital X. Now let's talk about forming your hypothesis. So once you saw this data and you have your prior experience, you are starting to form a hypothesis. Your hypothesis is that you believe that cats do not have special affiliations with phones, therefore I think that the cat didn't steal the phone, or I believe that clouds cause rain, therefore I believe that if there is rain, therefore, and condition that there were clouds, therefore the clouds caused the rain. I can hypothesize that a certain market predicate would or function would predict the market future. Okay, I can predict, I can have an hypothesis about how the market will behave. I have a hypothesis that my model is going to predict better what I'm trying to predict, okay? And all of these are hypotheses because we have some way of understanding the world, and we use this understanding of the world to make some predictions. In mathematical rigorousness, we denote these hypotheses with a capital letter H, hypothesis. H1, for example, is hypothesis number 1. And why number 1? Because once we get more data, we can go to H2 or maybe to H3, which are different hypotheses based on the data. And we say that H1 predicts the data capital D. Okay, for example, the probability that we'll see this data given the hypothesis H1 could be greater than the probability that we'll see this data given only our experience on the world. So let's say we think that the probability of seeing our cat and our mobile phone lost given the hypothesis that cats do like phone and our previous experience in the world is much greater than simply the probability of seeing this data that both our cat and our mobile phone is lost, given only that we have our prior experience without hypothesis number 1, which is that cats likes phones. Okay, when we say this is surprising or this is makes sense, this is like the probability. And now when you have formed your hypothesis, you start gathering more and more evidence into updating your beliefs. And when you update your beliefs, you might need eventually to update your hypothesis. Okay, because we have our hypothesis 1, and hypothesis 1 means that our cat has stolen our phone, but we said that the probability of H1 given pipe X, the large X, which is our experience in the world, is very low because we know that cats do not steal phones. However, now maybe you have found that your cat suddenly appears behind the refrigerator and he is coming to you. So now that you have this magical appearance of the cat, you might say, okay, so he didn't run away with my phone. Maybe he played with it, but maybe he didn't. And then you hear a phone rings from within your bag. So you can say, hypothesis 2, my phone is in my bag and my cat didn't steal my phone. And this is hypothesis number 2. And hypothesis number 2, you can say that it's very, it could be, it's very high because you actually heard your phone rings. But if your phone didn't ring and you only saw your cat, then you could still think that maybe he has stolen it. So in this case, this hypothesis would be simply a very low chance, but not as low as your cat ran with your phone. So when you see the additional data that we have spoken about, for example, your cat appears or you find that you hear your phone rings, then you have some updated data. Your data has updated. And once your data has updated, then the probability of the D given H1 hypothesis and experience on the world is changing from maybe very, very low to low or stuff like this. So you can have two hypotheses, hypothesis number 1 and hypothesis number 2. And then you check in order to decide which hypothesis is better, hypothesis number 1 or hypothesis number 2. You think about the probabilities. What is the probability of the data P of capital D given pipe H2 and our experience in the world, and you divide it by the probability of the data given hypothesis number 1. So if the probability of the data given hypothesis 2 divided by the probability of the data given hypothesis number 1 is like 10, then you know that you are sure 10 times that hypothesis number 2, which is on the numerator, is much more likely. So you might choose this hypothesis. And in any way, we can say that we measure, or we think about what is the probability of capital D, the data given our hypothesis, but we can reverse that also. What is the probability of the hypothesis given the data? When we talk about what is the probability of the hypothesis given the data, then we say that how well does the data support my belief, because this is the probability of my hypothesis given the data. So you think about how well the data supports. It's like what comes after the pipe. This is the supporting of how well what comes before the pipe. So if you do PH pipe D, then how well does the data support my hypothesis? And the reverse of it is P D pipe H is how well the hypothesis supports the data, because you are now asking what is the probability of the data. So to sum up what we have discussed, we have beliefs about the world and we call them capital X. This is our prior beliefs. We have the data that we observe, like we lost our phone and we can find it, we don't see it. This is capital D, this is the data. The probability of the data given the X, capital X, which is the probability of the data that we see given our experience on the world, is denoted by P D pipe X. Okay? And in order to understand the world, we of course rely on our beliefs and we form hypotheses, which we call H1, H2, H3. And the probability of D conditioned by our hypothesis plus the experience of the world, we can say that if it's much larger than simply the probability of the data given our experience in the world, then maybe our hypothesis strengthens the probability. So this means that our hypothesis might be true. And of course, we can formulate H1, H2, H3, H4, and then update our beliefs when new hypotheses explain the data better than the old hypothesis. And we do this by division. We do probability of data divided by hypothesis, probability of data given hypothesis 2 divided by probability of data given hypothesis 1. And this is basically the story. We have data, we have our experience on the world, and we try to come up with the probability of what is the probability seeing the data given our hypothesis. We divide with the hypothesis 1 and hypothesis 2, and we come up with numbers. So I hope you enjoyed this. I find this a very interesting topic. I think it's very important for software engineers, even when we try to find bugs and stuff like this, not only cats that steal phones. And I will see you next time.